Basic functions. Do y'all remember talking about family of functions? There's all those basic functions, and from there, that's when we started going into transformations, right? We went into shifting up, shifting down, shifting left, shifting right, vertical stretch. Remember all that?
Oh, yeah.
Okay. So, yeah, whatever. Yeah. Continuity. Anybody know what continuity means? Think about the word continuous. What does continuous mean? Forever. So a graph that is continuous, I could draw the graph from beginning to end without picking my pencil up. That's continuous. If I have to pick my pencil up, that's a discontinuity. Got a hole in it. Maybe it jumps. The identity function, we've talked about that. That's y equals x. Squaring function, y equals x squared. Remember, mathematicians are not very creative when it comes to naming stuff. Okay. A cubing function, that would be y equals x cubed. Good. Square root function, that would be y equals square root of x. The cube root function, y equals cube root of x. The absolute value function, y equals absolute value of x. Piecewise function, what were those? It's made up of pieces, right? And then we're going to talk about the relation x equals y squared. The relation x equals y squared is not a function, it's just a relation. We'll look at that. It's not, that's okay. Okay, definition of continuous. A function is continuous over an interval if its domain, if it's hand-drawn, can be sketched without lifting the pencil from the paper. That's it. If I can draw the graph without picking out my pencil, that's continuous. A function can be broken and can be continuous on certain domains instead of the entire domain. Okay. Here are two functions. It says describe the interval or intervals of continuity for each function. Look at graph A. What does graph A appear to be? Forever continuous. What kind of a graph is this? It's a quadratic, so it looks like y equals x squared. And what do you mean forever continuous? Okay. When we're talking about intervals of continuity, we are referring to, all right, let's draw some boxes today. We're referring to the domain. So don't tell me about going up. Okay? So letter A, on what interval or intervals is A continuous? On the x-axis, where does it start? Negative infinity. Okay, so this parabola, I understand you're saying it's going up, but isn't it also going right and left as well? It goes left forever. It goes right forever. So the interval of continuity for graph A, it starts at negative infinity and goes to positive infinity. And why do I put parentheses around those? Yeah, no one can tell me the exact value of infinity. If you can tell me the exact value of where this happens, then you would put a bracket. Okay. Part B, what do we see? Okay, it's a what? Describe the graph to me. It's a line with an open, with a hole. We actually call them holes. It's got a point of discontinuity. There's a point on this graph, there's an x value on this graph that is not defined. It does not exist. But does this graph have continuity? Yes. So reading from left to right, where does the graph start? Negative infinity. and it stays continuous all the way up to the x value of 3. Parenthesis or bracket? No. Because if you say bracket, that means the point 3 is included. Is 3 included? No. So how high does it go? Keep going until keep going until you get there. So can you get there? You can't get there. So parenthesis. You cannot tell me the exact value that the continuity stops. Okay, he was exactly right. It's 2.9999999, and we would all be dead before we finished saying all the 9s. Okay? But then it starts again. Where does it start? 3.000000000, at the very end there's a 1. Where's the very end? Heck if I know, right? So 3 to infinity. Any thoughts on that? Oh, good? Questions? Okay. All right, we're going to talk about several functions. Just kind of jot down the name of the function, maybe sketch the graph of it, and then make sure you write down the domain and the range of these graphs. The first we're going to talk about is called the identity function. It's called the identity function because if you tell me y, I'm going to tell you x is the same thing. So the identity function is y equals x. The identity function looks like a line with a slope of 1, because that's what it is, and a y-intercept of 0. X can be anything. Y can be anything. So the domain is negative infinity to infinity. The range is also negative infinity to infinity. Domain and range are up here. The line y equals x is continuous always. So it's continuous from negative infinity to positive infinity. Good to move on? Okay. The next function is the squaring function. The squaring function, like it says, is y equals x squared. It's a parabola. It has a vertex at 0, 0. Can you square any real number? Real number, can I square? Yes, I can square any real number. So the domain is all real numbers. X can be anything. What happens when you square a number? The answer will always be, or the answer can't be what? Answer cannot be negative. That means y cannot be negative. So the domain is all reals, but the range is 0 with a bracket, because 0 squared is 0, all the way up to infinity. This function decreases from negative infinity to 0. And as soon as it hits 0, it begins increasing until infinity. Something I noticed on the test, when y'all were talking about intervals of increasing, decreasing, or constant, some people wanted to use brackets. I'm going to say this again. When you're talking about intervals of increasing, decreasing, or constant, you will always use parentheses. Always use parentheses on increasing, decreasing, and constant. Okay. This function can be drawn without lifting up the pencil, so it's continuous on the interval negative infinity to infinity. Comments, questions on the squaring function? Okay. The next function is the cubing function. Y equals x cubed. Has a domain of negative infinity to infinity, and the range is also negative infinity to infinity. The cubing function is always increasing, so it's increasing on the interval negative infinity to infinity, and can be drawn without lifting of a pencil, therefore it's continuous for all x. The next function is the square root function. What can you not take the square root of? Negative numbers. Square root of 0 is 0. I can do the square root of 0. But I cannot, in the real world, take square roots of negative numbers. Therefore, on the squaring function, x cannot be negative. So the domain for the squaring function, the domain goes from 0 with the bracket, because I can take the square root of 0, so x can equal 0, up to infinity. And the result of taking the square root of a non-negative number will also be a non-negative number. So the range is also bracket 0 to infinity. What does that graph look like? I've asked you to describe it. Do what? It's like half of a parabola. That's exactly right. It's like someone walked up to x squared and like kicked it over and said, oh, you're not a function anymore, so they erased the bottom half. Okay, so let's look at this increasing interval again. Remember I told you, increasing, decreasing, and constant intervals are always parentheses. Notice the interval of increasing goes from 0 to infinity. Parentheses. The domain has a bracket because x can be 0. But you can't tell me that it's increasing when it started. That doesn't make sense. When it started, it just started. As soon as it passed 0, that's when it started increasing. So when did it pass 0? Well, at 0.000000, etc. to 1. It is continuous. Where do you start drawing it? You start drawing it at 0. That's why there's a bracket there. Does anyone have any questions about braces and brackets? It can kind of get tricky. Okay. All right, we'll move on to the next graph. The cube root function. Y equals the cube root of x. The index is a 3. The cube root function looks a lot like the cube function. Again, got kicked in the head and knocked over. And I guess it tumbled because if you kick it in the head and knock it over, you can't make it look like that, so it's got to flip over too. Okay. I can take the cube root of any number, positive or negative, doesn't matter. The cube root of -8 is -2. The index is odd, so the number inside the radical can be any real number. Domain, all real. Range, all real. This function, just like the cube function, is always increasing. So it's increasing from negative infinity to infinity. And again, it's continuous for all x. The cube root function. Am I going too slow, too fast? How's spacing going, guys? Talk to me. All right, don't talk to me. What a deal. The next function is the absolute value function. The absolute value function looks like a V. It has all the same properties as the squared function. I can take the absolute value of any real number. By definition, the absolute value is the distance from 0, and we don't measure distances with negative numbers. If I drive from my house to the school, it's 9.7 miles. If I drive back home, it's not negative 9.7 miles. It's still 9.7 miles either direction. Domain is all real, so negative infinity to infinity with parentheses. Range, it starts at 0. The absolute value of 0 is 0. So bracket 0, and it goes up from there, up to infinity, close parentheses. The absolute value function is decreasing from negative infinity to 0, again, parentheses only, and begins increasing at 0 up to infinity. I can draw an absolute value without picking up my pencil. The next function is piecewise function. And a piecewise function does not have all those nifty little rules like we did in the past, because every piecewise function is different. Every piecewise function depends on the individual pieces. In a piecewise function, you will be given the domain. This is your domain for this particular function. You might have to combine a bunch of things together to make it true, but that is the domain. So in looking at the domain of this function, the top piece exists from 2 to negative infinity, because it's less than, including the 2. The bottom piece goes from 2 to infinity, not including the 2. If you combine those together, what's the domain of this function? All real numbers, right? The first one says I'm going to go from negative infinity, kind of write this out. If I went from negative infinity, my board's freaking out on me, negative infinity up to 2, I put a bracket on that, meaning 2 is included, right? But wait, there's more. Union, not including the 2, up to infinity. Can you see that right here, that 2 is included? Does that make sense? 2 is included. It doesn't have to be included in both, but because 2 is included in one, 2 is included in the entire function. So if I combine these, the domain for this entire function is negative infinity to infinity. To figure out the range, well, we have to graph it. And if you remember when graphing piecewise function, graph the whole line and then erase the part that doesn't exist. Okay? So if I was going to graph this line, what does the graph of negative 2x plus 5 look like? That's all we're going to do is we're going to graph that. Y-intercept is 5 with the slope of -2, meaning from there go down 2 over 1, down 2 over 1, and so on. Reverse it. And then I could draw this line. Something like this. But that line has a domain of all real numbers. According to my function, I have a restricted domain. Where does that graph start? At 2. So if I go to the x value of 2 and then go to my graph, which is right here, will I put an open or closed circle? Why? Equal, it's closed. Perfect. Which side do I keep? Keep the left side. That's the way it's pointing, right? Right side gets erased. Graphing the line x plus 1. Y-intercept is 1 with a slope of 1. So it's going this way. And I'm not going to draw this line because it's going to, when I go to erase, it's going to cross. Where does this line start? This line starts at 2. Open or closed circle. I will go to x value of 2 up to my line, open circle. And this line exists to the right. So from there, I'll draw my line to the right. And since I do have a couple dots because I needed them to figure out where this line was starting, I'll come over here and erase them. Okay. So let's talk about some things about this graph. First of all, we've already established the domain. What about the range? Okay, so it starts at a y value of 1, and it can be 1 because that is a solid circle. And from there, the graph is going up to infinity. So there's my range. So basically the purple graph, that is purple, right? The purple graph basically established the range, correct? Because the green graph, remember, smashed into the y-axis, the green graph is accounted for. Okay, let's talk about continuous. When is this graph continuous? Is it always continuous? No, you can't draw it without picking your pencil up. So it's continuous starting where? Negative infinity, because remember we're talking about the x-axis. Okay. Up to 2. Is it continuous anywhere else? Hold on a second. That parenthesis was wrong. We're talking about continuity. It goes exactly to 2. Where else is it continuous? From 2 to infinity. Continuity. From the left side, it goes all the way to 2. And then it jumps. The instant it passes 2, it jumps up and continues to be continuous. When is this function decreasing? Negative infinity to 2. Parenthesis or bracket? Parenthesis. Increasing, decreasing, constant. Always parentheses. Period. When is this function constant? No flat lines? Okay. Increasing. Is there anything else in those other graphs that were mentioned that we haven't discussed? Okay. Let's do another piecewise function because I know you love them. Two x plus 3 if x is less than or equal to 0. Negative x squared plus 3 if x is greater than 0. Let's start by sketching 2x plus 3. First of all, what's it look like? A line. Simply a line. Y-intercept at 3 with a slope of 2, up 2 over 1, up 2 over 1. Back 2, back, down 2, back 1, down 2, back 1. Where does this line start? Starts at 0. Can it be 0? Yes. So at x equals 0, the line starts with a solid circle because it can equal. And it goes which way? Less than goes to the left. Something like that. Erase my extra dots. Next function, bless you. Next function, what's it look like? It's a parabola. What else can you tell me about it? Starts at a y value of 3. What else can you tell me? Negative, so it opens down. Perfect. Perfect. So it starts at 3, open or closed circle. Okay, I'm putting an open circle there because it's greater than 0, which means this parabola is only going to the right. Okay, and 1 squared is 1, so I'm going to go down 1 from my original point. Go back to my original point, go over 2. 2 squared is 4, down 4. Like so, down 9. So, looks about like something like that. Looking at the graph, what's the domain? Or looking at this right here, what's the domain? What can x be? Look at the picture if you need to. What can x be? How far to the left does it go? Negative infinity. Just to 0? Okay, so what's the domain? All real numbers. Because even that point at the very center is covered, right? I've got a closed circle, I've got an open circle, but they're both there. So the domain goes from negative infinity to infinity. How about the range? Low to high, always low to high. Where does it start? Where does it start? Negative infinity. Because we're coming up, right? Range starts at negative infinity and goes up to 3. Can it be 3? So, bracket. Let's talk about where is this graph continuous? Can you draw this entire graph without picking your pencil up? Yes, you can. Yes, you can. Because you're on the purple line all the way to 0, and the instant you pass 0, you're on the green graph. The instant you pass 0, you're on the green graph. So this is continuous from negative infinity to infinity. Let's talk about increasing. On what part of the domain is this function increasing? Negative infinity to what? To 0. Okay? Again, we're only talking about the domain. You're riding a roller coaster. I'm riding along, I'm going up. When do I stop going up? At 0. Right? What happens at 0? Start going down. The instant I pass 0, I'm now going down. So this is decreasing from 0 to infinity. Again, increasing and decreasing and constant. We only use parentheses. I think I've said that once or twice this class period. Maybe 3. Bless you. Okay. Next graph is my favorite. The greatest integer function. The greatest integer means exactly what it says. If I'm walking along a graph, what was the last integer I passed? The domain of the greatest integer function is negative infinity to infinity. X can be anything. But the output can only be integers. Hence the name greatest integer function. Well, if the output can only be integers, guess what the range is? All integers. Okay? So the domain is from negative infinity to infinity and everything in between. But the range is negative, really big number. -3, -2, -1, 0, 1, 2, 3. I'm only naming the set of integers. So looking at this table, if I'm standing right on -2, is -2 an integer? Yes. So the greatest integer of -2 is -2. I'm walking along the x-axis. I pass -2. -1 is in front of me. -2 is behind me. I'm walking in the positive direction. What was the last integer that I passed? -2. So the greatest integer of -1.5 is -2. I'm walking along. I just passed -1. I'm getting closer to 0. I just passed -1. I'm standing at 0.99. The last integer I passed was -1. That's why the greatest integer of -0.99 is -1. The greatest integers on the negative side is the part you have to think about. Okay? When you're positive, it's pretty simple. Get rid of the decimal, and that's the answer. The greatest integer of 0.001, chop off the 0.001, you got 0. The greatest integer is 3.99. Chop off the 0.99, you're at 3. You can graph the greatest integer function on the calculator, but it does not show you where the open and closed circles are. So here's the graph. This is called a step function. Again, mathematicians, very creative. Why do you think they call it a step function? Because it looks like steps. Okay? The greatest integer of 0 is 0. And I stay 0 until I almost get to 1, because the instant I get to 1, it jumps up to 1. That's why you have an open circle at 1 and a closed circle at 1. Okay? The greatest integer function is constant between 0 and 1, 1 and 2, 2 and 3, 3 and 4. So there's infinitely many continuous intervals. There's infinitely many discontinuous parts of the function. Okay. All right. We'll graph one. No, it's a bracket that has like a double stick on it. So if you started just plugging numbers in there, let's plug a 0 in there. Let's make a t-table. If you plug a 0 in, what would happen? 1/2 of 0 is 0. 0 plus 1 is 1. And the greatest integer of 1 is 1. Well, it is an integer. So the 0.01 is on the graph. Plug a 1 in there. 1/2 of 1 is 1/2. 1/2 plus 1 is 1.5. And the greatest integer of 1.5 is 1. So at 1, we're also at 1. If I plugged in, I don't know, plug in a 1/2. I'm going to squeeze in a 1/2 up here. 1/2 of a 1/2. A 1/4. A 1/4 plus 1. 1 and a 1/4. And the greatest integer of 1 1/4 is still 1. Okay, so we're still at 1 there. So we're still at 1. Let's go 3/2. A 1/2 of 3/2. It's 3/4. Remember, of means times. Of means times. And 1/2 of 3/2 is 3/4. And 3/4 plus 1. 1 and 3/4. And the greatest integer of that is still 1. Plug in a 2. 1/2 of 2 is 1 plus 1 is 2. And the greatest integer of 2 is 2. So magic happened. As soon as I got to 2, magic happened. I jumped up here. Okay, I see what's happening here. So it stayed until I got to that point, and then it jumped up. And then it's going to stay this. It looks like 2 spots there, open circle, and then it's going to jump up. And then it's going to stay, and then it's going to jump up. And I can do this backwards. I can jump down and go back to. I can go down and I can go back to. I will not be spending a lot of time on greatest integer functions. Okay? All right, I'm going to go ahead and stop right there. We'll wrap up 2.6 tomorrow and jump into 2.7. We're almost done with 2.6. Just another slide, I think.